Hi, everyone, and welcome back to another session of Shifting Gears with SDV. I'm your host, Luzmila Muña, and I'm excited to welcome our guest speaker today, Leonardo Rossetti, who will be presenting using AutoSD to develop and test Eclipse SDV Blueprints. If you have any question, please feel free to drop them in the Ask a Question tab or in the chat or directly in the chat. And with that, thank you so much, Leonardo, for being here and joining us. And over to you. Thank you.
All right. Hello, everyone. My name is Leonardo. I'm calling Leo. I work for Red Hat Automotive. I'm talking about how we have a new project called Eclipse AutoSD, which is used as an integration project to run other Eclipse SDV projects, blueprints, and so on. The overall agenda, I'll just go through the motivation behind the project, then I'll go through the details behind the project, the technology that powers it. Then I'll try to do a quick demo on how it works in practice, or how we plan to support blueprints in the whole Eclipse SDV working group, and so on. So a little bit about I'd say the problem statement behind all this is that as probably already know, there's lots of Eclipse SDV, not only Eclipse SDV, but overall open source projects around automotive, most of them being middleware or application framework focused. There you have several different operating systems around. Each operating system has their own flavor about how to deploy, package, and run applications. So how could, in particular case, how could the Red Hat platform reduce that gap, making it easy for different build systems and projects to be built and run together while providing a frictionless experience to project leads, person leads, and developers, and so on. We did have so Red Hat's initial solution was to basically use a tool called Automotive Image Builder. And package your applications with RPMs, which is the standard way for Red Hat to package and deploy applications and software in its operating system. The problem is that for every source code change, at least in the development workflow, it requires you to always repackage your software and then rebuild your application, because in AutoSD case, the packages included during the image assembling phase, which can take quite a while, depends on your CI/CD pipeline capabilities. And that's a very big, heavy workflow to do it just if you're changing a few lines of source code. It also means that you are not always going to be easily able to integrate with the RPM build system. I know that you have different build systems around. So you have Bazel, have other, maybe you are used to Ubuntu or not used to deal with RPMs. So there's kind of a gap in there, and each build system kind of forces you into doing things in their own way. So that's kind of a problem when you're trying to create a frictionless experience for different persons' projects to work together. I'm going to use Eclipse Core here as an example. We are highly loaded Eclipse Core. We're basically exposing our platform in a repository that they call RHIVOS Integration. So RHIVOS Integration is a repository in Eclipse Core that bundles all modules of the project together, and then you build them and you run them into different operating systems. So there's AutoSD, there's QNX, there's Kerberos for Electrobit, there's vanilla Linux with Ubuntu, and so on. So on the left, you can see um, the original workflow. So on a GitHub action, so for every source code change for that repository, you'd have to install Red Hat's image builder. You'd build then you'd build the RHIVOS integration repository, RHIVOS integration project. It could take quite a bit on a GitHub worker. Then you have to build an AutoSD QEMU image. Then you build RPMs. Then you start that VM, and then you send RPMs, and then you run tests over SSH. So that whole process took more than 20 minutes, but it's quite something. Then we moved to another technology. Instead of building everything from scratch on every PR, we use something called bootc, which I'm getting to details later in these presentations. bootc stands for Bootable Containers. So what does that mean? That means that instead of building an image from scratch, you just use a Bazel to build a RHIVOS integration repository, and then you just build you just include whatever artifacts are generated from that build into a OCI container. This is special. This is a special container because it requires certain tools to be inside that image, which are all bootc related. But we have a pre-built image for Xcore to do so. And then you just, but in the end, it's just an OCI. It's just an OCI image. So as long as you have a tool that's able to create an OCI image, such as Docker, Podman, there are Bazel OCI rules and so on. Then you can just again use a pre-built or an RSD image. You can use bootc to apply the operating system root file system changes through a bootc container, which I'll get in details later. So all we need to do is to build a container, start a VM, and apply the changes from this container, and then you're done. So that's a way faster pipeline, a way simpler, and also allows to be an end-to-end based integration where the previous workflow did not. So as I said, this is more of a summary for what I just said, but that brought the question in my head: could this workflow using bootc be applied for the whole Eclipse SDV working group? So could we apply the bootc methodology together with either Bazel or any other tool in order to, as long as we're able to build bootc containers for blueprints and other Eclipse SDV projects, that will allow us to create this fast experience for Eclipse SDV projects and blueprints to test their whole stack in AutoSD, which is a sub distribution of CentOS string for the automotive industry. So getting to this is the full name of the project. I just referred to the project as Eclipse AutoSD. That's faster to say. So a very high level explanation about AutoSD. There's we call the upstream downstream relationship. So everything that's in AutoSD comes from CentOS string, which gets a considerable amount of software from Fedora, which has a bunch of upstream software packages in it. So as you can see, whatever is RHEL or Red Hat. So the default RHEL distribution is generated from CentOS string, which is a rolling distro. And the same will go for Red Hat Developed Operating System, or RHIVOS for short, from AutoSD. So AutoSD is generated from CentOS string, and then RHIVOS generated from AutoSD. So you can consider that AutoSD is a downstream or sub-distribution of CentOS string. Now, if you expand roles and responsibilities of that infrastructure with the Eclipse AutoSD project. So you have the Fedora CentOS, which we call community infrastructure in Red Hat. You have the Red Hat infrastructure, which, although it uses the same tools, it's a total different and separated infrastructure. And then you'd have you'd be using the AutoSD tools and packages into the Eclipse SDV infrastructure in order to build all the required artifacts by the Eclipse AutoSD project. That includes all the RPMs available in AutoSD will be available in the Eclipse AutoSD project. You'd have base images built and distributed as artifacts for other projects to use as well. You inherit our MCO architecture. So in here, it's important to know that AutoSD is not safety qualified. It's QM only, but it follows the same architecture we have in RHIVOS. So although it isn't an open source certified Linux distribution, you are able to test your stack in a hypothetical safety architecture with a QM and a ISO environment. And you get a real-time kernel by default from AutoSD, and every target platform there is support. There's a few automotive boards around, such as some boards from Texas Instruments, for example, and a few others. And you are also we also support cloud platforms such as AWS and Azure, and basically you get all that support for free by if you want to deploy your AutoSD and run your stack on either on one of the automotive hardware that we support upstream, or in a cloud provider or virtual machines with QEMU. So a little bit in bootc. So bootc is a very complex piece of software, so this is a very summarized high-level explanation in the context of the Eclipse AutoSD project. So the idea of a bootable container is that under the hood has something called S3, which is it's a file system subsystem that allows you to run a Linux distribution with an immutable file system. How does that work at a very high level? It's basically your file system is managed as a Merkle tree, so it's kind of as a Git tree where the file system is immutable with the exception of a few directories. The idea here is that every change in the file system is as if you were adding a new commit to the tree. So you get the history of those changes. So if you add a new file, or edit a new file, or change the file permission, those things are tracked by S3. So every change gets its own commit, and we're able to roll back a commit if you need, and so on. So because it's basically a series of so it's a rootfs, which then every change is basically a rootfs tarball difference that gets applied into it. So that means that it's extremely compatible with the OCI image specification, which is also tarball based, which allowed Red Hat to create something called bootc, which basically allows you to get a container image and apply its layers on top of S3. So you are able to apologies. You are basically able to manage your operating system updates or changes from a container image. So what happens is which I'm showing at the end of the presentation in a hands-on demo is that we're basically going to use a bootc CLI in order to we're going to apply the layers of a container image that's hosted on a container registry into the AutoSD operating system, we're going to reboot, and whatever is installed in that bootc image is going to be deployed into our AutoSD operating system. An extra explanation of bootc. Bootc is basically a collection of CLI libraries and systemd unit files that allows bootc to do its magic. So here I'm just going to go through to the high-level explanation of the goals of the project, a little bit more of the goals of the project and what we intend to do. As I said, our main goal, our mission is to provide a foundation operating system for projects where they can build, run, and test their stack in a real, its operating system. It's the same operating system that's going, our product is going to be based. So this is a Linux distro tailored for automotive use cases, with several different technologies behind it, such as OS3, bootc, and other things. One thing, the base image contains the folder architecture by default. So as you can see in here, you have the just one thing about this image: you are not required to run things in a container. You can just run a binary directly into the either image or into the QM partition and run it. Or although we do kind of recommend use containers for DevOps experience in case you need to have a complex deployment, but putting several binaries and running on the host machine also works. As you can see, the main aspect of our mixed precursor architecture is that we have a QM partition. So there is an isolated QM partition that is run as a container. So you can put whatever you put. So there's a QM container that uses that QM partition as root address. So that's you have a QM isolation in both process through the container and at the file system partition level. So all your files are isolated because the QM partition contains all the libraries that would not be certified in RHIVOS, where the host environment outside of that partition container, you contain the bits that are qualified and certifiable in RHIVOS. Obviously, RSD is not certifiable, but as I said, the architecture is the same. So as I said, one of our main goal of this project is to provide base images. So whoever is using AutoSD and Eclipse SDV does not have to build it themselves. And for that, we use a tool called Automotive Image Builder, which actually it has a 3-phase process in order to provide those images. So first of all, it creates 2 container images. One we call builder images for both x86 and R64. The idea, so builder images, they contain the necessary bootc tools in order to build the bootc target images, which are also container images. The target images, they're called target images because you are targeting a platform and a build chose. So in particular case here, it only has Cream or Raspberry Pi, but whatever hardware you'd be building, you need to build a container image that is explicitly targeting that platform, whatever physical or virtual. Those are all parameters from the Automotive Image Builder, which is just a CLI. It's a CLI that's a kind of a wrapper of the bootc CLI. And lastly, so once you build the target images, the builder images, you are able to build your disk images, which are basically QCOW and image files. So what the tool does, basically, it gets your target image. So let's say you get the QEMU MD64 container image, which contains everything that your operating system that's going to run the hardware has to hardware to run using that target OCI image, and then you generate a disk image out of it. It's either a QCOW file or an image file. So basically, with this, we kind of almost reduce entirely the environment disparity, because you're basically generate everything from the same source. If you're using you can use the target image, the bootc target image to locally to run tests with tools like Dev Container. You can extend it to as you can use as a base image and as a parent image with like Podman or Bazel, and add your own stuff, and then either generate or use bootc to apply it into a base image. So you are basically using the same source for everything, rather than just having different. The usual approach is that you kind of have a container image that has the same tools, and then your operating system disk image is built from using different tools. In this particular case, everything is built is the same tool from the same source. So you have a guarantee that wherever you have access to the target image, you are able to do it. You'll be having in your automotive hardware. So as I said, one of the main goals of this project is to provide a way. We want to create. So I want to create specialized OCI images for each blueprints or custom integrations, or to run different Eclipse SDV projects together. So we're basically going to use the base target bootc images, and then apply. So let's say if you wanna have a base OCI image with a score, you're gonna have one, and then you can just apply that into existing base disk image. Or if you wanna have a custom deployment, so let's say you wanna deploy Eclipse and Kaios, and then you wanna deploy some custom. You wanna get part of some modules from the Eclipse core. You wanna get the whole stack. Then you create a custom. You extend the base bootc target image with your own stuff, build it and push it to a registry, and then you're able to apply it to an existing disk image, or you can generate a disk image yourself. There's something that we don't have anything around it. That's more of a proposal, or maybe a call for contributions. There's anybody interested in this sort of things. One of the main problems that I've seen that's hard to solve in automotive is test your software into a real automotive hardware, or maybe specialized virtualized virtual machines. There are some companies that they specialize into providing specialized VMs that emulate automotive hardware on the cloud. Red Hat has a tool called Jumpstarter, which is, if you're familiar with Eclipse OpenDut, it's a very similar. Maybe the usage is a bit different, but the problem is trying to solve the same. It allows you to connect to do hardware automation. So basically, you are able to power on a device that's either in your desk or in a remote lab, flash operating system, run tests, and shut it off. I would like to eventually, for the Eclipse OSD project, to enable to do this kind of a federated lab integration. Maybe something to work together with the Eclipse Eclipse OpenDut project, to allow any Eclipse SDV project maintainer to basically deploy something in those labs and run tests in a real hardware, automotive hardware device. That's always allow that kind of obviously that requires for companies to step up. That's Red Hat included, to try to expose some of their hardware to Eclipse. But I think it's a very interesting problem that needs to be solved from the so Eclipse SDV projects. They are able to kind of do all the required testing here on real automotive hardware. Last but not least, we also want to create some tooling. So I'm particularly interested in basically, create a tool that I see that several blueprints they use Docker Compose in order to as a way to define how their full stack should run and work together. So maybe you can have some kind of a CLI that's able to parse that compose file into whatever manifests files that AutoSD needs in order to deploy it in our AutoSD image. Or maybe there are other opportunities, but it's more of any tooling, maybe something that's not tightly coupled to Eclipse AutoSD, maybe it could be something more generic, but tooling that allows you to easily deploy blueprints in different operating systems, including AutoSD. This is more of a high-level workflow, very generic and abstract in a sense. How we would be using the project, which I'll be showing shortly. So your tooling can vary a lot as long as your tooling is able to do OCI building. So Bazel is able to do it through an OCI rule module. You can use Podman or Docker. You should be able to do dev containers to do local development using the RSD image locally with VS Code. Then you basically you push forward to eventually you push just Containerfiles somewhere. You publish that image to a container registry, but you're also able to generate through CI archive to do the updates on the RSD image as well. And the last step would be to kind of start the RSD image somewhere like QEMU or the hardware, and use bootc to deploy your custom container image and then test all your stuff together. Okay, so this is the part where I'm going to I will stop sharing and share again. This is the heads-on part of this presentation. Okay, I have this repository. It's published. It's published on GitHub. I'll share. Hopefully the font size is big enough. So what I'm going to show here. So basically, I'm going to show how the project is used. So I have two folders here. So basics contain basics examples of what I just said. So if I check this, so first checking this Docker file, as you can see here, first I'm using a base CentOS string image to build a very simple Hello World project, and then this is the bootc image I was talking about. So our repository builds and publishes base container images in the GitHub registry. So you can basically use it as a base image, as a bootc image. I'm just copying a single artifact, could copy a full folder, and so on. I'm also copying a basic systemd service file to run that application, and here I'm basically. So basically, every change that you're doing here, from this point on, will be applied into the actual RSD operating system image. I already have that image built. I'm not going to build that image because I already have that image built and published in Kiro.io. So here now I'm downloading the QEMU disk image also from the project. So you don't really need to build anything from scratch besides your own software. It's archived with XZ because so the image is as lightweight as possible, so not having a network. So now I'm going to, I don't need that much memory. AIRS just stands for Automotive Image Runner. It's just a wrapper script to run Twinboo, so not much big a deal. Just booting should take very long. So our image is a root. Just default username is root. Default password is password. It's just development purposes. You're not supposed to use this in production. So that's why it's used this dummy user and password. So as I told you, there's a bootc CLI. If you do bootc status, here you can. This is basically your. It's the initial comment because this is a clean image that doesn't have anything. So in order to in order to apply our container image file system changes in here, you do a bootc switch, and then you specify a container image. So you can see, so it's downloading it's a downloader apply out. So what's happening here? bootc by default to check which layers were missing between your local operating system and the remote container image. In this particular case, my QCal image is older than my container image. So it means it's downloading all the layers that I'm missing from in my operating system that are available in my container image. If you generate the thing right at the same time, you'll just be missing one or two layers because they'll be synchronized. So it basically loads deploys. It's going to deploy that through the OS3 CLI. One thing that shows updates, they require, because it's an immutable file system, it requires you to reboot your OS. As you can see, it's good for next reboot. So I'm just going to reboot using systemd. So, and then log it again. So if I run bootc status, now you can see this is my new comment. It's unversioned because it's just a development container image. So you can see that there's a new update here. If we do still status pull.service, this was deployed by, as you remember, by my container file. You see that the service has been run. It basically creates a this file in here with it's just a C permit that writes this file into the TNT folder. And as I said, you can also, in case you want to, something goes wrong, you want to roll back, you can just do bootc roll back. It will basically roll back to the previous comment. You can also use the apply for both bootc switch and rollback. If you use the apply optional argument, it will apply the container changes and will reboot automatically. In case you are lazy enough like myself, I don't want to write system reboot every time. So we do that again. If you do bootc status, you see that our previous image is still here, but so you can roll back again. It's kind of switch A and B kind of thing. But there are ways for you to configure to remove the previous deployments if you want. And then basically I'm back to my original deployment. So, but you can see my temp file is not, it's not here. And I have no sample service file. And also, just to demonstrate, for demonstration purposes, if I do switch again, so you see the image is already here, nothing has changed, so it just redeployed the image. So it's smart enough to not re-download all the layers. And if I just reboot, and it should go back to the previous custom. So and again, I should have, so see the sample image, sample message file again. If you do bootc status, as you see, just swapped over again. So that's basically the main function. So you'd have you can also deploy container quadlet files, SDV files. You can pull container images from in your container file. Whatever you do in the container file gets applied into your operating system. Another maybe another interesting use case, for the sake of time. I'm not going to build a Bazel project because it can take a little bit. I'm just going to show what I did here. In here, we just have the same sample C project that writes a file. Here I have a build instruction that builds that sample C file. Here we just have the module definition. Here I'm using RHIVOS toolchain from Score, and as you can see, I'm using RHIVOS from Bazel. I'm here pulling my base AutoSD bootc image, and the magic happens in the images folder. So in the image folder, you can see in here, first I have a simple target, which basically builds it's basically building my sample application and packaging it into a tarball. That tarball then is referenced into this OCI image rule in Bazel. This basically creates a container image using my base boots image image as default, and applies. It basically creates layers to apply the sample CLI artifact and the systemd service. So with this, I'm basically using OCI images as the specification in order to build or apply custom software into a base RHIVOS image. It doesn't matter what tool you use, as long as you have something that's able to generate OCI images. Another thing that I like to showcase here in Blueprints. So I have this still early stage. I'm applying all that with this search to signal blueprint. So I have a bunch of files in here. Basically, what I have in here is a bunch of systemd unit files in order to create and run. So one thing is that this search to signal is all containerized. So all those files, they are actually building and running containers. And I have a small script to check if everything is good. So just to demonstration purposes, so let's say, for example, we have the Xeno router container. It basically this is a systemd AutoSD systemd feature where you have a new container section in a systemd unit file where you can specify your container, how to run a containerized workload with systemd. So in particular case, you run a Xeno router, use the upstream image that's hosted on Docker Hub. there's nothing particular in here besides mounting volumes, running exposing a port, and so on. Another things that is that in here, so not because it's a blueprint, not all our images are published or pre-built and available in a container registry. So for Zenocooks supervisor again, you have in here you see it's using a local image rather than a remote one because it does not have a pre-built image. And how does that work? Because you use systemd so in here you see it is depending on this build service for the same application, which is this one. So in here you have a build section, which basically it's going to build the Zenocooks container. It is a work directory that defines the container file it's supposed to run. So it's going to on system start once the system is booting and has enough resources to do so, it's going to build its container. And once the build is done, it's going to start it. It's going to start its the container source counterpart, and that's basically true for every other .build .container file. So I'm going to run to remove again. I already have an image built for that for that blueprint. I don't think I'll be able to run it because but I can at least show how. So I'm gonna bootc switch apply. So this is my service to signal container. As you can see, just putting 2 layers, as they're all built from the same base bootc image. So you just need to apply extra 2 layers in here. Once that it's going to automatically reboot, and then once it reboots, it's going to start building containers, which I'm not going to showcase in here because it's going to take forever to build all those Rust applications in my VM, and I think my screen probably freeze if I if I do it. So if I do status, assuming that so see, actually it failed to probably because it failed to push it to pull the image from some network problems by VM probably. So here you can see Zeno is running, and then we have, so for every so if you check in here, so you know there's a few networking problem here. Because it basically built the things in a it used this upstream Rust image in order to build. I think if I just do a restart, it should work. It's probably something to do with the order that the things are being started. I think if I do start, so I can see this is the log of the thing that's being built. You can also use journalctl in order to inspect any container log. So if we do it's actually because it's still copying the image, so that's why it's not showing anything. Oh, here, sorry, here we go. So here you can see it's copying. Eventually to start building, and then that's true for every other service. So that eventually the thing will be around. Here is my CLI. Let's say that the consider broke's not ready because it still has to build everything in order to run. And the idea is to do that for every other blueprint that's around. And useful for hackathons and so on as well. And that's my full presentation. I will maybe the sharing. Let me share my slides again. This is our. We have a Slack channel in Eclipse SDV. We have this GitHub org, and Eclipse AutoSD is our main repository with issue trackers and where all the files are located right now. I would I'd like to thank you for the time here, and I'll open for questions if any.
Thank you so much, Leonardo, for that amazing presentation and demo. We do have a question. Our colleague Diana already answered it, but if you want to say something else about this, about the Eclipse Automotive Integration for AutoSD as an existing project infrastructure of Eclipse Foundation and SDV project, right?
Okay. Yeah, as I said, we have a Slack channel. Feel free to drop by or message me directly in the Eclipse SDV Slack instance as well.
If anyone has another questions, please feel free to write them right now in the Ask a Question tab or in the chat before we wrap up. And in the meantime, I will quickly thank you so much for sharing the links, Leonardo. We also will share it in the post email that we send to all the registrants to this webinar. So no worries, we will share it again. And I wanted to share, we are doing a survey and we would like to have your insights. So please feel free to participate. There are some prizes to win, and we would love to know your thoughts about the community and the ecosystem at Eclipse Foundation. So thank you so much for participate. All right. It seems that there are not any more questions. Let's see. Let's wait a little bit. All right. It seems that we don't have any more. I wanted to thank you again, Leonardo, for sharing your knowledge and expertise with us today. And we would love to have you again in other different opportunity here as a SDV community and for upcoming webinars. So thank you so much for all the attendees as well. And see you.
For the opportunity, to a pleasure.
Thank you. Bye-bye.